also define or write the parametric equations of a line in space. Actually, you guys already know how to write them for a line in the plane. That's what you learn at the end of calculus 2. So, but we're going to take a different approach. By the way, a vector approach, not a parametric, so to speak, approach. We will write the Cartesian equation of a plane in space. We will graph planes in space, in a little bit of 3D graphing, and find distances between a point and a line, a point and a plane, between two planes, angles between planes. We will do a lot of stuff, a lot of analytic geometry, so to speak, in space. Okay, so let's first of all, going back to calculus 2, when you represented an equation, or rather a function in its parametric form, so you define two equations, x equation, a y equation, and well, the easiest way to parameterize any function is to give the variable t to the independent variable. That's not always the case, because if we get to equations that do not really represent functions, like a circle, well, you use trigonometric functions. And what else? Ellipses, well, you need also trigonometric functions with different coefficients. Hyperbola as well, you would use hyperbolic functions, right? So that's again the origin of hyperbolic functions, points that are on a hyperbola, and also trigonometric functions. Those are functions that are on a circular pattern, right? So that's the origin of it. Well, so we're going to get into the vector approach. For the first time, we're going to start with the easiest, which is the line. Okay, so what are we going to do? We're going to add a third component. That's for the z component, all right? And in the same way that parametric equations, gives you the position, it's essentially a collection of points for different values of t, of a third variable, third party variable, rather, that's what I was to say. So, well, in this case, it's technically a fourth party variable, because we already have the three variables x, y, and z. So that new variable governing the set of points is going to be t. And for the sake of simplicity, essentially we will describe these vector valued functions as the position of some particle, whatever the size of the particle is, at different times t. Because it turns out that time is not the only parameter. Later on we will discuss the distance parameter or the arc length parameter. All right, how do they look like? Well, so essentially we're going to go from parametric set of parametric equations to vector valued functions. So this x of t, y of t in the plane, x of t, y of t, z of t, or in the ijk representation. And so we will be working on both notations, by the way. So now here's a picture here. There's a picture where we have the 3D space, and then we have this line in black right here. So that's the line. All right. So that's the line with an equation that we'll describe in a second, where, well, we're going to have a fixed point, an initial point technically, which is x naught, y naught, z naught. And then we're going to have another point, which is any other point on the line. Can be on that position or in the reverse position, either way. But what about these vectors that we see here? So what does the vector idea have to do with the line right here? Well, it turns out that all these order triples, and these are not order pairs, we're talking about the space, these order triples are terminal points of vectors in standard position. For instance, this other point, I can plot another point. This point right here, it's the terminal point of this vector in standard position. That means a vector whose initial point is the origin. Okay? So now, here's the thing. It's a line. So technically, there has to be a slope, all right? The problem here with the line, we don't have a slope, a rise over run, in the same way we would have for the equation of line y equals mx plus b. So rather than say rise over run, dive over run, no, we're not going to go like that, because the rise over run, then we need to be specific about which direction. In the direction of the xy plane, in the direction of the xz plane, or in the direction of the yz plane. So we would need to look at three different cases, which complicates the problem slightly. I mean, we're going to get into those perspectives later, called the traces of a function, but well, that's later. So in this case, since we're not going to go rise over run, because think about this space. I mean, think about this space. So you are a point in space, right? Unless you're just going in the direction of the xy trace, so that'll be valid somehow. But you can rise, run, and then go down. So it's kind of hard to describe that. So that's why instead we are this line right here. This line in space is going to have this vector in green that I'm highlighting. So that's what we called a direction vector. So rather than this line in space being governed by a slope, rise over run, no, it's governed by a direction vector. So I'm going to start at a point, and then I'm going to go in the direction of, say, 1, 4, -3, and then follow that same pattern. So in a way, it's like a rise over run, but it's not as easy as rise over run. All right. I think this looks familiar. I mean, x0 plus at. Doesn't that look like y equals mx plus b essentially, where m is multiplying the variable t, and the constant term is the intercept? Well, is the y-intercept? Well, in this case, it's not the y-intercept, the x-intercept, the z-intercept. So this x0, y0, z0, it's going to be the initial point that we will be given, and this component, or this coefficients a, b, and c, are going to be the components of the vector that directs the line, giving us as a result our first vector valued function right here, which is the line in space. How are we going to obtain a line in space? Well, let's have a look at our first example here. So our first example in the next page. Well, so find the vector equation and the parametric equations for the line L that passes through the point A equals 3, -1, 2, and B 0, 5, -3. Okay, so let me open GeoGebra. I'm going to need it for later. Okay, so also I need my GeoGebra files. Anyway, okay. So where t corresponds to t equals to 0 corresponds to point A, and then we will modify the vector equation to represent the line segment, to represent a line segment. Keep in mind the line segment, it's not the same as just a regular line. A regular line extends forever in the negative positive order. I mean, for all values of t. So and then they're asking us what value of t, what t value represents point B. Well, let's do one thing at a time. Well, so to describe a line in space, we need an initial point, which we're given, that's point A. And we need as well a direction vector. We have 2 points. We can do terminal minus initial to describe that that direction vector. Okay, let's do some label here. So let A be having coordinates x0, y0, and z0. All right. So that's going to be our initial point. And so this describing the vector AB. That'll be, okay, terminal minus initial, 0 minus 3, that's -3. 5 minus -1, that's 5 plus 1, that equals to 6. And -3 minus 2, that's -5. Okay, what is this? Let me do another set of labels here. This is going to be our A, our B, and our C. Those are going to be the direction numbers or the coefficients of the variable t that will direct the line. All right? So I'm going to write the vector valued function in terms of parametric equations first, and then I'm going to change to the vector valued function notation. All right. So let me start with the general form, that is x, which is x0 plus at y that equals y naught plus bt, and z which equals to z naught plus ct. All right, and we have everything we need. So this x naught, y naught, z naught are the coordinates of the initial point. That is 3, -1, and 2. And then a, b, and c are the components of the direction vector. That is minus 3t plus 6t minus 5t. Right? So that is our vector valued function in parametric form. Okay, let's turn this into vector notation. Okay, so I'm gonna write this simply as r of t, like f of x. Right, so this is the first time we introduce functions in function notation, like f of x, but this is on r of t, which is in component form. That is 3 minus 3t, -1 plus 6t, 2 minus 5t. Okay? So that's how it looks like in vector notation. Now, here's the thing. When you work on your homework, you may see a different notation, so to speak. So this is what some exercises do as far as format. So what they do is they write a separate vector with the initial point, with the numbers with the initial point, -3, 3 plus +3, -1, and 2, plus t times the direction vector, that is -3, 6, and -5. So I guess they do this to resemble the y equals mx plus b, so to speak. I guess that's why they do that. But I guess it's shorter to write the first version. But just know that when you do the homework, you will see the two different formats. Okay. So, here is the thing. When we write a vector valued function like this, this is essentially valid for all values of t. That is, for t being in the set of all real numbers, right? Think of these lines. Do you have restrictions for a line? A line is defined for all values of t. In the next chapter, we will get to find domains of these vector valued functions where these components are no longer linear expressions, like inverse trig, rationals, or radicals. So everything you learned back in pre-calc and intermediate algebra is going to come back. All right? So, okay, there's a part B, so to speak, for this problem. They're asking us to modify the vector valued equation, the vector valued function, rather, to represent this as a line segment. What's the difference? Well, so this is just a line. When I see this, when I could have written I wrote that t belongs to the set of all real numbers, or else I could have not written it. If I don't write anything, that means it's for all real numbers, or at least in its domain. However, when we modify this to represent a segment, that is, it's a limited, it's bounded. So we need to write this equation instead. R of t. So the same vector valued function, 3 minus 3t, -1 plus 6t, and 2 minus 5t. But in this case, I need to set a condition. What's the condition? Well, that t goes between 0 and 1. So, and here is the thing. Every time you parameterize a line using the initial and the terminal point of two given points that represent initial and terminal, this can be represented as a segment that goes between 0 and 1. And well, you don't have to do the following. I'm going to show you the following just to convince you in a way. All right? So, change color for this. Okay. So, that means that if you evaluate r of 0 and r of 1, if you evaluate these two, okay, that is 3 minus 3 times 0 -1 plus 6 times 0, 2 minus 5 times 0. So that's going to give us the vector, okay, 0, 0, 0 here, 3, -1. And what's that? 2, all right? Well, but this is a vector here. This one is a vector right here, all right? So, but again, keep in mind that these vectors are vectors in standard position whose terminal point is going to be point A, which is 3, -1, 2. All right? What about R of 1? So for R of 1, substitute, evaluate this at 1, 3 times 1, -1, plus 6 times 1, 2 minus 5 times 1. Okay? What is that going to give us? Okay, 3 minus 3, essentially, that's 0. 6 minus 1, that equals to 5. And 2 minus 5, that equals to -3. Isn't that a vector whose component is the same as the coordinates of the terminal point? Right? So this is just to show that indeed this is the point. All right? So that is, what's that? 3, 0, 5, -3. All right? Of course, I mean, there's other ways to parameterize lines. If you Google some other ways, you can you can modify this equation right here to represent not only the interval 0 to 1, maybe -5 to +7, but you would need to play with these numbers right here, and it gets more complicated. So for this class, we're going to parameterize lines using the initial and the terminal point. We're going to do this a lot, and that's the approach we're going to take at the end of the course when we get to line integrals, when we need to parameterize smooth piecewise functions. So, well, you'll see when we get there. Okay, let's have a look at another example. Write an equation for the line segment. Notice it says line segment, not for the line. When it says line segment, that means we need to specify this restriction or this domain, t going between 0 and 1. Okay, so again, we are given 2 points, P naught, P1. Let's find the vector, the direction vector, P naught, P1. That is 3 minus 2, that equals to 1. -1 minus 5, that's a -6. And 4 minus 6, that equals to -2. So that's our direction line. So to speak, our slope. Well, again, there's no rise over run in this case, right? We're going in the direction of a vector starting at an initial point. Okay? So, again, R of t will be given by x naught plus at, y naught plus bt, and z naught plus ct. Okay? What is x naught, y naught, z naught? So this is x naught, y naught, and z naught. So that is those are the coordinates of the initial point. What is a, b, and c? These are a, b, and c. The components of the direction vector. Let's just substitute. I mean, it's very formulaic. As you can tell, it's very formulaic. All we need is add, subtract numbers. So x naught, that's 2 plus a, so 2 plus t, comma 5 minus 6t, and z naught, which is what's that? 6 minus 2t. Right? But I'm missing something. I'm missing t being between 0 and 1. All right? Because this is a line segment that describes the line only for the initial and the terminal point. Okay? All right. Oh, I think I forgot to graph something. Okay, let me open GeoGebra. So I want to show what we are doing essentially. So. Okay. So this is what we're doing here. This is what we're getting. So I have used the curve command right here to plot, or rather to grab the line 3 minus 3t for example number 1, and negative 1 plus 6t, 2 minus 5t, and then the last three inputs here are the t by itself, which is just to declare the variable that we are working on, and the limit, which is 0 and 1. Well, as a result, I got this line in space. Okay, let me put the perspective, the x, the what's that? The x, y, and z perspective, the usual perspective textbooks do. All right. So, notice I'm plotting only the line that goes from 0 to 4t, going from 0 to 1, which corresponds to initial point and terminal point. Okay, so these points are the terminal points of two vectors in standard position. This vector and this other vector. Of course, I could keep going and add another point, for instance. Okay, let me see how can we modify this. Well, so what if I want to go from, instead of 0 to 1, I'm going to go from 0 to 2. Okay, so I'm going to get a longer line right here, and I'm going to we can also describe the vector that takes us all the way to point 2. So again, all these points on the line right here corresponds to the points that are terminal points of vectors in standard position. That's what gives the direction of the line. Though again, there's no such thing as rise over run, because it's the space. It's no longer the plane like in Calc 1, Calc 2, or algebra, right? Okay, so that's a visual of what we're doing. Let's go back and look at another more interesting problem here. So, they're asking us to find the equation of a line in vector form, no longer in parametric form, passing through the origin that is perpendicular to both of these two vectors, u and v. Perpendicular to two vectors. What do you think about this one? So in this case, check this out. In this case, we don't have 2 points to describe a vector, right? To get terminal minus initial, so we can get the direction vector that directs the line. So this direction vector, we should get it in a different way. In this case, they're giving us 2 vectors, but they're telling us that direction line, it's perpendicular to these 2 vectors. How should we get that direction line? Add them together equal to 0. Any other ideas?
Dot product?
Dot product. Well, the dot product would output a scalar, right? So, and we need a vector to get those components that direct the line. So you're close? What is that? The cross product. Because the cross product between 2 vectors is going to give us a third vector that happens to be perpendicular or orthogonal to the 2 vectors, and that's the condition that we need to obtain a vector that is orthogonal. So that means, let's set this cross product u cross with v. That'll be, okay, I, j, and k. So 1, 1, 5, 0, 4, 0. Okay? And the result of performing this cross product, I don't want to spend the whole lecture doing the cross product. I'll just give you the result. That's going to be negative 20, 0, and 4. Okay? So what is this vector? This vector has the components a, b, and c that are going to be the coefficients of t in the equation of a line. All right? Well, we already have the most mysterious part of the piece of the puzzle here. Everything else we already have. We have the initial point. This one is x naught, y naught, and z naught, right? And it's all zeros. Okay. So let's write r of t again. That equals x naught plus at, y naught plus bt, and z naught plus ct. Okay? So let's just substitute the values. So x naught, y naught, z naught, they're all zeros. Nothing to substitute there. So that equals, okay, That's going to give us A, which is negative 20 t, B, which is, okay, that's going to be 0t, and ct, that's going to be 4t. Well, we can simplify this a little bit by 0 times c, that's just 0. Okay. 20t, 0, 4t. So this is our final answer in this case, right? And in this case, notice they're not telling us find the segment. They're just asking us to find the equation of the line, not the segment. So no need to write any conditions unless you want to write t is for all real numbers, which is fine. So t going between negative infinity and positive infinity. That's another way to write all real numbers. But it's not necessary. When you just see the word line, that implies all real numbers. Otherwise, if it's the line segment between two given points, then you need to specify the interval. And in fact, we wouldn't be able to specify an interval because we're just given the nature of the situation here. We're just given an initial point. We're not given a terminal point. All right. So there's no way we can get the terminal in a way. All right. Now here is the thing, and this exercise is designed this way for a very specific reason. So there's something we can do about this. So number one, R of t. I'm going to factor out the t, okay? That's going to give us negative 20, 0, and 4, all right? And well, one thing worth noting here is the components of this vector. So do you guys agree that we could reduce to lowest terms? Because all these components are multiples of 4. So actually, that's something we can do. So rather than having all these big numbers, this is the same as saying t divide everything by 4. We get negative 5, 0, and 1. I know the components look different, right? However, it doesn't matter if you write it in the smallest integers possible or in large integers. So because essentially that is we're factoring in a number, a constant multiple, but the direction of the line doesn't change. All right, that just makes the direction vector to be twice as long or half as long. So another way to represent this, well, if you want to divide by 2, fine. Negative 5 halves, 0, 1 half. Or divide by 4 or divide by 17, that's fine. It's still going to be the same. It's still going to go in the same direction. We're still going to, the direction is not going to change. Okay? So these 3 answers are going to be acceptable. Question?
Shouldn't we write the scalar next to the vector?
You could, but not. You don't need it. But you could write it. You could write it down. Mm-hmm. So that's all it does. Stretch or make the vectors a bit smashed. All right. So it doesn't matter. Okay. So the 3 of them, I'm going to box the 3 answers. All right. What's next? Find the intersection between 2 lines. Let's get more algebraic here. All right. So we're given 2 lines. An R of t line, 3 plus 2t comma negative t, 5 plus t, and an R of s. I mean, the variable doesn't really matter. So I'm using 2 different variables just to make a distinction. So when we do the algebraic process, we don't get the same variable. Otherwise, we would be in trouble here. All right. So how do we find the intersection of these 2 lines? So here is the thing. Let me highlight the components with different colors. So number 1, let me highlight the x components with the x components, y component, and z component with z component. So this is what we're going to do. Again, we're going to use that fact about 2 vectors are the same if their components are equal. So that's why I'm color coding the components for this. To set the x component with the x component, the y component with the y component, and the z component with the z component. Okay? And we are going to create a system of equations with two equations, two unknowns. Well, there is three, right? No. We will need the third one for later, but at least we will create a system with the first two first. So you'll see how that's going to work. So number one, so let me create the system. That is 3 plus 2t equals to 8 plus s, in accordance with equating the first two components. On the other hand, equating the green components, that means negative t equals to 2s. So let's solve this system of equations, and you may use your favorite method of solution. You may use elimination, substitution. You may want to arrange these equations, so you can use matrices on your calculator. It doesn't matter what method you use. Try to be as efficient as possible. And in this case, well, the variable t, it's pretty much solved, so we can do a substitution. So let's take advantage of that. So this is what I'm going to do. Number one, I'm going to solve for t right here and call t equals to negative 2s. Okay, so that's what we are going to substitute. Let me highlight it first. And then I'm going to substitute in the first equation here. So that's going to be 3 okay, I'm going to do it here. 3 plus 2 times negative 2s equals to 8 plus s. And well, the rest of the problem, it's a basic linear equation. 3 minus 4s equals to 8 plus s. I'm going to move all the s's to the left hand side and all the constant values to the right hand side. So subtracting s on both sides, that's going to give us number one, 3 minus 5s. Okay, here's where I have a little issue with my writing. Sometimes my 5 look like s's or vice versa. If something is not clear, please raise your hand. That's fine. Let me know. Okay, and that equals to 8. And then I'm going to subtract through the 3 on both sides. That's going to give us negative 5s equals to 5. That means s equals to negative 1. All right? So that's s equals to negative 1. Okay. What are we going to do with this s? I'm going to substitute it in the first equation I solved for a t. All right? That means t equals to negative 2 times negative 1. That means t equals to positive 2. All right? Okay. This is not the final answer yet. Okay. What did we just find? Well, we just found the times s and t at which the two lines cross, but that's not the question. The question is, what is the intersection point? Not when do they intersect. Okay. So what are we? Oh, number one. Before finding that intersection point. So here's the thing. All this process may not be valid at all. Despite the algebra and the arithmetics, everything made sense. We still need to verify these values of t equal to 2 and s equals to negative 1 in the equations in blue, that is the z component. So we need to verify the z components. That is, I'm going to do so z. Okay, r for little r, that's going to be 5 plus t. So I need to substitute 5 plus 2, which equals to 7. And for big R, R of s, or R of t, let me do R of t, R of s, big R of s rather, that's the component 4 minus 3s, where in this case I'm going to substitute 4 minus 3 times -1. So that makes it a 4 plus 3, which equals to 7. So when verifying the z components, these two results must be the same, right? Otherwise, number one, double check your work when solving the system of equations. Or number two, these lines are not intersecting at all, right? So that's what it would mean. They don't intersect because it has to be valid for the three components, right? Okay, now that we have the validation, so to speak, we may proceed to find the point of intersection. And here you have two options. Number one, either, so intersection point, you may either evaluate lowercase r of 2 or big R, uppercase R of -1. You don't have to evaluate both, just one of them, all right? I mean, if you want to evaluate both, then that's fine, okay? So that's going to give us, well, I'm going to do R of 2, little r of 2 rather. So that is 3 plus 2 times and -2, and lastly 5 plus 2. That's going to give us the following, okay, 3 plus 4, that equals to 7, and then -2, comma 7. But hey, check this out. This is a vector, all right? They're asking us for the point of intersection, not a vector. Again, let's recall that these points on lines represent terminal points of vectors in standard position. So the correct way to express this is as an order triple. 7, -2, 7. All right? Okay, there's another piece of information. I didn't type it, but this is what you're going to see on the homework. So you will be asked whether these two particles collide or not collide. So, because what do we have? So we have two lines, right? We have two intersecting lines like this where particles are traveling at a given rate, okay? So it is possible that the two particles go through the intersection point at the same time. What's going to happen? Well, they're going to collide. How do we know if they collide or not? Well, so we need to compare these two results for S and T. If those two values are exactly the same, that means the particle along the line R of T, it would be passing through the intersection point at the same time as the particle going along R of S. But in this case, since these are different values, they're crossing the intersection at different times. So that's why they are not collide. They're not colliding. So do not collide. Particles. Okay? So these two particles are not going to collide, right? Unless we had t equals to 2, s equals to 2, or t equals -1, and s also equals to -1. So if we had a timer, so to speak, that means the particle going along R of t is going through the intersection point after 2 seconds, while the particle going along R of s is going through the intersection point -1 that is 1 second before. That's kind of weird for a negative time, but even though it's s, technically it's also time. So we're just using two different variables to distinguish between the two vector valued functions. All right, equations of planes. Now let's get into something different. Now that we define lines, now let's define equations of planes. Okay, so we're going to consider a plane containing a point, so any point, x naught, that we're going to call x naught, y naught, and z naught. Okay, let me highlight that. What else? And it contains a vector labeled n. Okay, we're going to label this vector n, that is perpendicular or normal to the plane. All right. So visually, okay, so if I have this plane right here, so this vector has a direct. I mean, this plane has a direction vector, so that actually forms a 90-degree angle with the plane. All right. So that those are the two pieces of information that we're going to need to describe the equation of a plane. Well, let me draw a picture. So number one. So this is our plane. Oops. And we're going to have what's that? A point P naught, which is x naught, y naught, and z naught. Okay? And what else? So this point right here will also be the initial point of that vector that forms a 90-degree angle with the plane. That is, again, in other words, it's orthogonal or normal to or perpendicular to the plane. Okay? And this vector, it's actually that's why they're using lowercase n to denote that the vector is normal to the plane. All right? Okay, so this vector will contain the components A, B, and C. All right, so we have the equation at the very bottom, right? The two forms, the standard form and the general form. But I'm going to derive this equation, actually. Rather than just, hey, here's a formula, let's describe where is this coming from. Okay, so number one. Since this vector right here happens to be orthogonal to the plane, okay, that means that this plane, we need to get a vector that is on the plane, not perpendicular to the plane, not like slant to the plane, rather on the plane. That means a vector like this. You know, this vector is on the plane. This other vector is also on the plane. This other vector is also on the plane. Well, I just need one vector. Well, what are the components of that vector? Well, those components are going to be obtained from the same initial point that's contained on the normal vector and any other random point on the plane. Let me call this point Q. And this point Q will be another point x, y, z. Not anymore x naught, y naught, z naught. So because again, there's pretty much infinitely many choices for those points Q, x, y, and z. All right. Of course, there's a perspective here, right? But hopefully you guys can see that this green vector that it's on the plane forms a 90-degree angle with the vector in blue that directs the plane. Do you guys agree with that? Okay, otherwise, well, let me show you with the planes right here. So that is the direction plane. And well, this other vector is to describe any vector on the plane. This is a vector on the plane, another vector on the plane, another vector on the... You have infinitely many choices for that, okay? There's no limit for that. All right, so... Okay, so how are we going to go from this geometric situation to an algebraic equation? Okay, so here, let's get the algebraic expressions for this vector. So number one, let's describe the vector PQ, or rather P naught Q. How do we get that vector? Well, terminal minus initial, x minus x naught, y minus y naught, z minus e naught, right? So, x minus x naught, y minus y naught, and z minus z naught, all right? And then we have the second vector. So, that is n, which is a, b, and C. Okay. How can we use this information to get to this algebraic expression? Let me give you a little hint. Let me circle this 0. That 0 is going to give away Somehow it's going to give away the idea. Another piece of information that is going to give away the idea, it's the fact that these two vectors are orthogonal. All right. So orthogonal vectors, something equal to 0. What about it? I think I just gave it away with that, right? I think I just did. Looks like you got it.
Dot product.
The dot product. What about the dot product?
If two vectors are orthogonal, we get a product of 0.
Exactly. So that means I'm going to set the following vector equation: P naught Q dotted with the normal vector, set it equal to 0. Okay? That means P naught Q naught, which is x minus x naught, comma, y minus y naught, z minus z naught, dotted with ABC, vector ABC, and set that equal to 0. Okay, so let's get rid of the vector notation by performing the dot product. Again, the dot product between two vectors outputs a scalar, and that equation right here that we have at the bottom of the page looks a hell lot of a scalar, right? No, there's no vector notation at all. Okay, A times x minus x naught plus B times y minus y naught, and C times z minus z naught. Let that be equal to 0. So that's our equation of the plane in standard form. So it's just a result. It's a basic result. I mean, the result of a very basic geometric situation, right? Thinking of two vectors being orthogonal, boom, that's the dot product being equal to 0. All right? Okay. And well, of course, if you distribute this A times x naught, and then you will obtain other constants here. You will obtain the AX, BY, CZ, that is this left-hand side of the general form. However, this constant times a constant, constant times a constant, constant times a constant, it will be a bunch of constants that will add up to, guess what? Another constant that you can move to the right hand side of the equation, which is going to be that constant. All right? So all you need to keep in mind right here when obtaining the equation of a plane is that here the coefficients of x, y, and z represent the components of the vector that is perpendicular to the plane. All right? The constant value, well, we get it from the other given point from the plane or any other information. All right. How about we see this in action with one example? Okay. They're asking us to find the general form of the equation of the plane containing the point, these 3 points. Oh, we're given 3 points right here. And, okay. We're not given vectors, actually, right? We're not given vectors. How are we going to do this? Okay, let me draw a plane. Just any generic plane. Actually, I'm going to show you the result in GeoGebra when we get the result. Okay, so this is the equation of the plane. So we're given 3 points, 3 random. Well, they're not random points. They're actually given points, defined points. Let me call this point A. Let me call this point B, and let me call this point C. All right? We need to get the vector, again, the vector that is orthogonal to the plane, right? Because again, that vector that is orthogonal to the plane is going to give us the coefficients of x, y, and z. How can we get that normal vector to the plane, given those 3 points as information? Any ideas? All right, so to get this normal vector, so we have enough information. That is, the vector that goes from A to B and from A to C, We define those two vectors. Their cross product is going to be a vector that would be orthogonal to that plane, right? So, and that's going to be the direction vector for the plane, which will be the coefficients of x, y, and z in the equation. Okay, let's get to it. Number one, let's define these vectors AB, AC. Of course, you can do it in a different way. You can do BA and BC, or you can do CA and CB. It doesn't matter. It doesn't matter because regardless of how you do it, you're using the same 3 points from the given plane. Nothing is going to change unless you make a silly sign mistake or something. All right? So just double check. All right. So the vectors AB and AC. So AB, terminal minus initial, I'm going to go with points. Well, actually, they're not labeled. Let me label them. That's A, B, and C. I mean, we can label them in alphabetical order. I don't see why not. All right. So AB, okay, 2 minus 3, that's negative 1. 0 minus negative 1, careful, that's positive 1. And 6 minus 5, that equals to 1. The second vector AC, that is, okay, go to point C. 1 minus 3, that's negative 2. 4 minus negative 1, that is 4 plus 1, which equals to 5, careful. And 2 minus 5, that equals to negative 3. So we're good to go. Set up a cross product, all right? Set up that cross product. AB cross AC. That is, okay, I, J, and K, and set the components, the other two rows rather, which are the components of the given vectors. That's negative 1, 1, and then negative 2, 5, negative 3. All right? And again, I'm going to skip the process for the cross product. I'll just give you the answer so we can move quicker. Okay, so that'll give us the vector negative 8, negative 5, negative 3. So those are going to be the components of this vector. So this vector is the vector n. Let me label it. This is n. The vector in red right here. The direction vector of the plane, if you will, whose components are going to be the coefficients of the variables x, y, and z. All right. So I think we can get the equation already. Okay, let me write the general form first. I mean the standard form. So we start from standard and then we end up with general. A times x minus x naught plus b times y minus y naught plus c times z minus z naught, and let that be equal to 0. Okay. A, B, and C are going to be those numbers negative 8, negative 5, negative 3. Okay, so negative 8, x, I'm going to leave a space for a reason. I'll show you in a second. B will be minus 5, rather, times y minus parentheses, plus c times, that's another negative 3, times z minus, well, let me get rid of the minuses. Oh, you might ask yourselves, what is going to be our choice of x naught, y naught, and z naught? Because in this case we have 3 points, right? But again, in this case, since those 3 points are on the plane, it doesn't matter what point do you choose. You know, okay, you can relate this to when you find the equation of a line, right? When you were given 2 points, what do? Find the slope between the 2 points, because you need the slope, and then choose any of the 2 points to write the equation of the line, right? Did it matter which point did you choose? Same here. It doesn't matter what point do you choose for the equation of the plane, all right? So I'm going to use point A. That is x minus 3, and then y minus negative 1, which makes it a y plus 1, and z minus 5. All right? So that's the equation in standard form, but they're asking for the equation in general form. That is, we need to do all the distribution, all the combining the like terms, etc. That means I'm going to distribute negative 8 times x, that's negative 8x. Negative times a negative, that's positive 24. minus, so that's a minus 5, y minus 5, and then minus 3, z, negative times a negative is positive 15, and let that be equal to 0. Okay, let me put the variable terms first. That's negative 8x, right, negative 8x. What else? Minus 5y, and minus 3z. And combine the constants together. 24 minus 5 plus 15, that's equal to 34. Set it equal to 0. But the general form of the equation asks for the variable terms on the left-hand side and the constant term on the right-hand side. That is negative 8x minus 5y minus 3z equals to negative 34. Well, notice how everything is negative on both sides of the equation. Turn everything into positive. It does, you could leave it like this. That's fine. But it's better to get rid of those negatives. That's fine. So that's the equation of a plane. Of course, how about we visualize this in GeoGebra? Okay. Okay, that's example number 5, I think. Yep. So what do we have? We have 3 points, right? We were given 3 points, A, B, and C. Okay. So right here, these 3 points. What did we do with these 3 points? We created vector AB and vector AC in order to find a vector that is orthogonal to those 2 vectors, which will contain the components of the direction of the plane. Okay, so that is vector. Okay, let me put another point. That's D. Okay, that's A. That's this vector that is orthogonal. Okay, does that look orthogonal? It does, right? Orthogonal in this direction, orthogonal in this other direction. So it works. So now I'm going to have the plane to show for us. And here is the plane. Here is a plane containing, let me see if I can. Okay, here it is. See how the points are on the plane, right? And see how that vector, that direction vector, is orthogonal. It forms a 90-degree angle with the plane, all right? So here, this is a good way to verify our work, all right?